Hi, I'm Dr. Ohania Gold, and this is Science on the Street. In April, we celebrate Earth Day, the annual tradition of thanking the planet for sustaining us and doing what we can in 24 hours to make up for the damage we cause on the other 364 days. In today's episode, we'll talk about how climate change has affected the oceans and land and how vital the atmosphere is to our existence. Except that's not Earth, it's Mars, with an ocean, the way it could have potentially been early in its history. This is Earth. And even though both Earth and Mars are about 4.5 billion years old, they have radically different climate and geological histories. So this Earth Day will be giving Mother Earth a much-needed day off, which is, and this is true, what every mother wants for Mother's Day. Instead, we'll discuss how Mars ended up with such a different climate from our own home. It all started around 4 billion years ago. The gas cloud that formed our solar system began to rotate and condense, forming balls of matter that bumped into one another and accreted into larger and larger bits. As these bits orbited, they swept up anything in their path, kind of like a celestial Katamari Damacy. These large masses became the ancestral planets we are familiar with. Together, they orbited a larger, hotter central mass that coalesced into our own sun. When the sun got massive enough, it began to fuse hydrogen atoms together, releasing energy as a steady stream of radiation called solar wind. The solar wind pushed lighter elements away from the planets closest to it, hence why the inner planets, Mercury, Venus, Earth, and Mars, are rocky and dense, and the outer planets are gas giants. Well, ever since Pluto got demoted. Very 2020 of you, 2006. As each planet spun on its axis, the heavier elements sank towards the center, forming the core, and the lighter elements stayed towards the surface. The innermost part of the core solidified while the outer core stayed liquid, spinning faster than the outer layers of the planet. The spin of that metallic liquid generated an electric field called a dynamo that allows the planet to have a magnetic field surrounding it. This magnetic field protects the planet from the solar wind emitted by the sun, kind of like the way an umbrella protects us from rain, except instead of rain, it's ionizing radiation. As time went on, however, Earth and Mars suffered radically different fates. Our own planet kept its core rotating, kept its magnetic field, generated a thick atmosphere from volcanoes releasing gas, water cycling and other processes, and eventually had the perfect conditions to spawn life. While the core kept spinning on Mars, off-gassing from volcanoes developed into a thick carbon dioxide and water atmosphere. Even though climate models during this time show global temperatures around freezing, regional seasonal temperatures may have gotten warm enough to melt local ice. The melting released groundwater from the southern highlands into the northern lowlands, forming an ocean, but possibly only for 100 days or so until it froze over. After a few 100 million years, the core stopped spinning, possibly because the planet is smaller than Earth and cooled off faster. That halt destroyed the magnetic field and therefore the protection from the solar wind, causing a real-life version of a sci-fi movie disaster. Where was the unobtainium when Mars needed it? Without the protection of the magnetic field, the frozen ocean sublimed into gas, and the bombardment of solar particles stripped the atmosphere and water vapor off of the planet, leaving it cold and dry. Today, Earth's climate models can't cool the planet enough to stabilize atmospheric conditions, but Martian historical climate models have the opposite problem. They cannot figure out how to get the planet warm enough to predict large amounts of liquid surface water for geologically long periods of time. So even though Earth kept its magnetic field, liquid water, and atmosphere enough to sustain life, similar conditions never existed on our rusty neighbor. So this Earth Day, when you look up at the night sky, take heart in knowing that we aren't being constantly irradiated by the sun, thanks to our enormous dynamo and its magnetic field. To learn more about Martian climate, we talked with Dr. Ashwin Vasavada, project scientist at NASA's Jet Propulsion Lab. Welcome, Ashwin.
Hey, great to be here.
Can you tell me a little bit about your research?
Sure. Yeah, I'm a project scientist at the Jet Propulsion Laboratory in Pasadena, California, and I work at a place that runs a lot of robotic spacecraft for NASA. So my research involves working with robots that explore other planets, particularly a rover called Curiosity that's on Mars right now.
So Curiosity is one of a number of rovers on Mars. How many are there total now?
Currently, there's 2 rovers operating on Mars and a few other landers, actually, and a bunch of orbiters. So we got a whole fleet of robots exploring Mars currently.
So you have some in orbit taking, I presume, photos and other sorts of analyses from space, and a few roaming the planet taking samples and things?
That's right. And, we count on those orbiters also to relay our data back to Earth. So we all the robots all work together at Mars as well.
How long does it take for those messages to come back to Earth?
It takes somewhere between like 7 and 20 minutes, depending on how far Earth and Mars are away from each other as they orbit the sun. And that's by the speed of light. So it's pretty far.
So as a geologist, I know that on Earth we can use ice cores and geological records to tell us about historical climate on our planet. What can Martian rocks tell us about Martian climate?
We're very interested in the first sort of billion years of Mars history. And fortunately, unlike Earth, where plate tectonics has erased a lot of that early evidence, on Mars, like these rocks that you see behind me in this picture that Curiosity took, those rocks date from that time period of 4 to 3 billion years ago, when we think there was a lot more water on Mars. And these rocks were laid down in lakes, some of them, and some of them were laid down in dry sand dune fields, but it's all turned to rock. And so by studying these rocks and kind of inferring geologically what the conditions were like when they were first deposited, we can understand that early climate.
Something I find really cool about being a geologist is that we can learn so much just by looking at the different structures that are recorded in the rocks, and it's really interesting that those same processes are happening on other planets.
Yeah, it's remarkable. That's one thing I've really taken away from the almost 10 years that Curiosity's been roving across Mars, is just how Earth-like it is. I live in Southern California near the Mojave Desert, and I can walk out and see many of the things in the Mojave Desert that I end up seeing also on Mars. Even though it's a different planet with slightly different gravity, there's a lot of similarities too. The rocks are kind of made out of the same things. Physics works the same way on Mars, and you end up getting a lot of the same structures that, like you mentioned.
In getting the rovers ready to ship off to Mars, were they tested in environments like the deserts of California?
Yeah, in certain degrees. So the actual rover that's on Mars now never left the clean room at JPL because it has to be kept very clean, because we're trying to look for traces of organic materials to see if there was any evidence of life, for example. So we didn't want to get that one dirty. But we took another rover out, and actually several different types of rovers, many of the instruments. We went out and tested in environments that are similar to what we expected on Mars. An interesting little side note there is, on Mars, gravity is only 1/3 of what it is on Earth. So when we tested the ability to drive over things like sand dunes, we actually built a full-size Curiosity rover, but made out of stuff that made it weigh 1/3 as much. So it would actually have the same weight on Earth.
That's incredible. I had never actually considered that you'd have to test it at a weight that would be similar to what it would experience. So you mentioned that you have sensors on that for testing organic life or traces of organic life. What was the result so far? Anything interesting?
Yeah, so far a big zero in terms of like actual evidence of past life. But on the other hand, Curiosity wasn't really built to detect past life as much as understand whether the conditions ever could have supported past life. It's a little bit of a nuance, but at the time Curiosity was built, like 15 years ago, we didn't really have the technology to confidently put a life detector on Mars. So we put a lake detector, if you will. We looking for evidence of ancient water, carbon in the rocks that could support life. And the Perseverance rover that's on Mars now, which looks a lot like Curiosity but is more advanced, that one actually has more ability to directly detect past life, especially when the samples it's collecting come back to Earth one day.
So there are plans in the future to pick up these rovers and bring them back?
Just the rocks that Perseverance is collecting. So the rovers will never come back, but we hope that in the next 10 years, we'll send a follow-up rover to kind of go in Perseverance's footsteps, collect the rocks that it packaged up into little tubes, and bring those rocks back to Earth so that the best laboratories on Earth can really look for that evidence of ancient life.
Awesome. That's very cool. You mentioned sending another rover up, and I know that some of the wealthier members of our societies are hoping to send human explorers to Mars. What's your opinion of trying to colonize Mars in general?
I sort of have two minds. I think in one sense, I feel it's inevitable because humans are kind of restless and they want to explore. We didn't really have to go to the bottom of the ocean or to the North Pole or the top of Mount Everest, but we want to. We feel it's important for us to expand our presence out, and Mars is a natural extension of that. In terms of colonizing, that's where I kind of differ from some of the rich people you were mentioning who see it sort of as a second home for Earth. I was thinking about, how I think about this. And to me, it's almost like, yes, we could do that, but it's kind of like living in my car versus living in my house. And you can live in your car, but it's not that comfortable. It's pretty hard. I'd rather make my house better and make it so it lasts longer.
Part of the issues that come with trying to colonize Mars are that there's no protection from the solar wind and radiation from the sun. Do you have an idea of why the dynamo ended and why the magnetic field disappeared on Mars?
Yeah, it's the details are still a little bit mysterious, but the big picture, I think, is you can simplify it down to just running out of energy in a sense. In order to keep the dynamo active, you have to have a fluid that has a metallic nature to it convecting inside of Mars. And like on Earth in my kitchen, if I want to boil water, I have to heat it from the bottom, and that creates the convective currents. On Mars, is the same thing. You either have a core that was hotter than the mantle, that's probably what you had, that drives that convection, and it's shut off, maybe because the core got cooler or the mantle got too warm, and you just lost the ability for that temperature difference to drive the convection. The details of that are still being worked out, but that's kind of the big picture. And ultimately, it's because Mars is also a smaller planet. Mars has more of a surface to enclose a smaller mass, and that heat coming off from the surface means that it cools faster.
Looking into the future, what do you think Martian climate will look like or be like in the next few million years, say?
Yeah, interestingly, Mars looks kind of like a dead, frozen planet now, especially compared to what it was maybe 3 or 4 billion years ago when there were streams running on the surface and lakes. For the past couple billion years, it's just been a dry desert with ice caps at the poles. And right now, it kind of looks like it's frozen in that state forever. But actually, over the time scale that you're mentioning of a few million years, the planet wobbles on its axis quite a bit. And sometimes the sun ends up hitting where the polar caps are now. And a lot of that ice moves actually to like the equator. So there's some interesting ice ages that go on Mars that are much more extreme than on Earth. So that's the kind of thing that happens now on Mars. But overall, I think its days of being like a wet and friendly planet to life are probably in the past.
I still think that on the first human mission to Mars, that they should send a paleontologist. I think that's the key to finding ancient life, potentially.
Yeah, it's always better to, I think, have the brain on the planet as opposed to like the brain behind the computer 100 million miles away from the planet. There's a lot of debate about whether you send humans to Mars to do science or not. And it's way more expensive and way more risky to put a human on Mars. But I agree with you that a paleontologist on Mars could do their science so much faster and probably better than a robot.
Is there any other tidbit or a little interesting fun fact you want to share?
Yeah, this sort of is borderline fun, but more practical. So the past couple of years have been crazy for everyone. But an interesting tidbit now is that we're continuing to run Curiosity from our living rooms on our laptops, which we never would have thought was possible before the pandemic. But we're still doing it now. And I think that's just an amazing achievement by our team. And I'm glad we figured out a way how to do it.
And bringing a whole new meaning to working from home.
That's right.
Well, thank you so much for being with us on the show today. This has been Science on the Street.